All right, fantastic. We should be all ready to go for pre-calc. I just delivered to you a bunch of assessment information, so hopefully that made sense. That's why our recording is going to be slightly shorter today than normal. But again, good morning. This is Wednesday, April 1st. Hopefully everybody's having a great Wednesday. Happy April Fool's Day. Today, what I'd like to teach you is our third and final topic related to this idea of the law of sines, the area of triangles. The third one is called the law of cosines. So that's really going to be the main focus of today. If anybody has any questions on the previous homework assignment, the one that was due today on law of sines, I am dedicating my office hours to answering those questions because I want to make sure that I teach this as much as I can today and give you as many examples as I can. But if you do have a question on that, please feel free to come during those office hours. That's 1:30 to 2 o'clock today in the afternoon. Come on by and we'll talk about as many problems as you want to talk about. All right. But our last idea in finding more information about triangles, be it the area of the triangles or missing sides and angles, is something that's called the law of cosines. And the law of cosines relates to this, which is a good friend from geometry that you may remember, called the Pythagorean Theorem, right? The Pythagorean Theorem from geometry states, everybody should know this, that if you have two legs of a right triangle and the hypotenuse called a, b, and c respectively, then a squared plus b squared is equal to c squared, right? So you should be able to figure out the answer to this. Did anybody find the length of the missing side of the triangle? Did anybody figure it out? What would be that missing length? Here's your opportunity. What do you got? What are we looking at? One side's 8, one side's 15. Little Pythagorean theorem. What are we looking at for that third side? Oh boy. Oh boy. Oh dear. I was going to say faith in humanity slowly declining. But Alejandro bringing it right back. He says in chat, 17. Absolutely. This would be 17, right? You would do 8 squared plus 15 squared is equal to c squared. Oh, Adam said it first, by the way. He did. He beat you by like literally 2 seconds. Good job, guys. Good job, both of you. And then you'd solve from there, right? You'd say 8 squared is 64, 15 squared is 225, and that's equal to c squared. And so you add those together, you're going to get what? This is 289 is equal to c squared, and so c is 17. Okay? Make sense to everybody? Now, that's all well and good in a geometry setting, right? Right triangle, Pythagorean theorem, no problem from there, right? But now, what if, given the same triangle, instead of saying this was 90 degrees, I now said that this was 89 degrees? You might be like, well, rats. I can't use our good old friend the Pythagorean theorem anymore because Pythagorean theorem really only works for right triangles. However, there is something that's called the law of cosines, which works for any triangle. And the law of cosines, just like the law of sines, is something that it relates to the Pythagorean theorem. That's why I put it up here right away. It's something that can be used to find the missing sides and missing angles of any triangle. Typically, the law of cosines is more complicated than the law of sines. The law of sines is usually a lot faster and a lot easier. So typically, I always say that to find the missing sides and angle measures of a triangle, start by using law of sines, if possible. So if you have a triangle problem and it's like find all the missing sides and angles, and you could use the law of sines, then use the law of sines. The law of sines is a lot easier. It's a lot faster. It's a lot more intuitive than the law of cosines. However, there may be specific cases that you cannot use the law of sines. The specific cases in which you cannot use the law of sines, be like, however, you need the law of cosines in these cases. Okay, oops, I meant to do a colon here. In these cases, the first case is if you're given an angle with two sides. So if I'm given this, right, then I need to use the law of cosines, because if you notice, I won't have anything that's across from each other in the triangle. I can't even use the law of sines because I'd be like, nothing's across from each other. There's no starting point, right? The other case in which we need to use the law of cosines is if I'm actually given three sides, right? So if I'm given my three sides and no angles, then once again, there's nothing across from each other. We need to use this idea of the law of cosines. Now, the law of cosines specifically is a special case of, actually this is really not true. I should say the Pythagorean Theorem is a special case of the law of cosines for when the angle measure happens to be 90 degrees. This is what the law of cosines looks like. It says, this is the law of cosines. That to find any side, c squared, if c is one of your sides of the triangle, it's equal to the other two sides, a squared plus b squared. You might be like, well, that looks really familiar. Then minus 2ab cosine of c. Okay? And that works for any triangle. Of course, manipulating this equation, you can solve for side A and side B as well. You could say, well, a squared is equal to b squared plus c squared minus 2bc cosine a. Or you could say that b squared is equal to a squared plus c squared minus 2ac cosine of b. As long as this side that you're trying to solve for matches up with this angle right here, you can manipulate these however you want, right? The letters are just stand-ins. They're just variables, okay? And if you notice, it really, like I said, looks a lot like the Pythagorean Theorem, because the Pythagorean Theorem is a special case of the law of cosines in which your angle C just so happens to be 90 degrees. Think about it. If angle C is 90 degrees, this right angle right here, then what's the cosine of 90? Well, the cosine of 90 is 0. So 0 times all of this stuff just goes away, and you're just left with a squared plus b squared. So what's cool is that the Pythagorean Theorem really is just a special case of the law of cosines. When you've done your Pythagorean Theorem problems in the past, you've really been doing the law of cosines all along. You just haven't realized it. All right, you just haven't realized it. But now that we're deep into the trig part of things, we can use our law of cosines to find missing sides and angles of any triangle. Like I said, the two situations in which we need to are if you're given two sides in an included angle, because nothing's across from each other. And same thing here if you're just given all three sides. Notice that you'll never have a situation in which you're just given all three angles, because then it's actually impossible to determine what the side lengths are. You could have a big triangle with the same angle measurements as a little teeny tiny triangle. How do you know which is which? That's why angle, angle, angle is something that's used for similarity and not actually determining side or side lengths or anything like that. All right, so anyway, let me show you an example of both of these cases. Suppose that I have an example like this. Ready? Here's my triangle, ABC. Suppose that this means that this is B, this is A, and this is C. Suppose that I told you that B was 3. I told you that A was 7, and I told you that angle C was 35 degrees. Well, if you notice, just like I kind of pointed out, nothing is across from each other in this particular situation, right? You don't have that same idea of like where to start for the law of sines, like nothing matches up here, right? So I have to use the law of cosines to solve for this side across from angle C. So I have to start by saying, well, c squared should equal, I'm just going to use this law of cosines, equals a squared, which is 7 squared, plus b squared, which is 3 squared, minus, a little bit of math here, 2ab cosine of c, which is 35 degrees. Okay? So I just use my law of cosines formula to go ahead and get started. I say now that c squared should equal, I'm just going to clean up everything. This is 49 plus 9 minus 2 times 7 is 14 times 3 is 42. Cosine of 35, right? Again, just combining like terms, c squared should equal 49 plus 9 is 58 minus 42 cosine of 35 degrees. A very, very common mistake here, and this happens in Algebra 2 as well when we deal with radicals. Something that a lot of people are tempted to do is they're tempted to take this 58 and subtract the 42. But remember, this 42 is stuck to this value of cosine. It would be just like if you said 58 minus 42x. You wouldn't combine those like terms, right? You wouldn't detach the 42 from the x. And the same thing is true here. So let's just go ahead and isolate that. Maybe by actually just plugging this into a calculator, right? We can just go ahead and say, well, c squared should equal, let's use our handy dandy calculator, 58 minus 42 cosine of 35. I get that c squared is about 23 point, we'll go to 1 decimal place, so we'll say about 23.6. And then we could just go ahead and take the square root of that, square root of 23.6, and it comes out to be that c is about 4.9. All right, just rounding to 1 decimal place there. Does that make sense to everybody, how we were able to figure that out using this law of cosines? Hopefully it does. Okay, so now that we know that c is 4.9, now I can just go ahead and finish my problem by using the law of sines. Okay, so now that I used my law of cosines, you can now finish using the law of sines. So we have to start here, and we can then finish using our law of sines, because now I have a pair that's across from each other, so now I can just go ahead and keep going. All right. One piece of advice that I want to give you is that when you finish this problem using the law of sines, what you want to do is you want to solve for the acute angle first. And I'll show you why that's the case. And by the acute angle, I mean the small angle. Since 3 is the smallest side of the triangle, B would be the smallest angle. So I want to go ahead and solve for that acute angle first, because then there will be no ambiguous case coming up or anything like that. Typically, when you do the law of cosines, the ambiguous case, like that we saw with those different angle measures, will not show up. So you do not have to worry about the ambiguous case when you start a problem by using the law of cosines. All right, that's a very important idea. So now what you want to do is you want to find the acute, or really the smallest angle first. The one that you know is going to be acute, because it's across from the smallest side, right? That's a good connection back to geometry. The smallest angle is across from the smallest side. I'll actually show you what happens if you don't do that in just a moment, okay? So you want to find that acute or smallest angle first. Again, note the ambiguous case will not occur. So you don't have to worry about the fact that you could have one solution or two solutions or no solutions. All right, we're just going ahead and trying to fill in the rest of the triangle. So to actually find the acute side, let's go ahead and use our law of sines to say the sine of 35 over 4.9 should equal the sine of b over 3. Cross multiply, you get 3 sine 35 degrees should equal 4.9 sine of b. I'm going to divide both sides by 4.9, so you get 3 sine, hopefully you can still see it at the bottom here, yeah you can, of 35 degrees over 4 should equal the sine of b. I'm going to go ahead and take the sine inverse of both sides, so I'll do that using my fancy calculator here. We're going to do the sine inverse of 3 sine 35 divided by 4, and I get 25.4, we'll call it 25.5. So we'll say that this means that B is equal to 25.5 degrees. All right. Now that I know that, we can go ahead and find angle A just by doing your 180 degrees minus 35 and minus 25.5. So I can do 180 minus 35 minus 25.5, and lo and behold, we get that angle A is 119.5. which, by the way, these would make sense for angle measurements because the largest angle should be across from the largest side, the middle one should be across from the middle, and the smallest one should be across from the smallest. Okay? Any questions, comments, concerns on that? Something that you don't want to do is you do not want to find the large angle first. Here's what's going to happen if you do that. So here's what not to do. You do not want to do this. All right? If you find the largest angle first, if you said, right back over here, you tried to find angle A first. You said the sine of 35 degrees over 4.9 should equal sine of A over 7, right? You actually went through the process of solving this. You would get 7 sine of 35 degrees equals 4.9 sine of A. You would divide both sides by 4.9 over 4.9 is equal to sine of A. You would take the sine inverse of both sides, and your calculator would tell you, I'll do it right now for you, 7 sine of 35 divided by 4.9. Oh, sorry, I got to do sine inverse of all that. We want to do the sine inverse of 7 sine 35 divided by 4.9. And your calculator would tell you that angle A is 55.02 degrees, right? Which would then imply that angle B were 180 minus 35 for angle C minus 55.02 for A. That would mean that angle B would have to be 89.98. But how could angle B be that huge angle? Because it's across from the smallest side. Do you see how that answer doesn't make any sense at all? Because angle B can't be the largest angle. It's across from the smallest side. It has to be the smallest angle. So this is the type of stuff that can happen if you do not solve for that acute angle first. You can get answers that really just don't make any sense. Okay? So always, 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 when you do a law of cosines problem, start by finding the side across from the angle you're given. Then finish using the law of sines, but find the small angle first. Once you find the small angle, you could be confident by saying, oh, that's an obtuse angle, which makes sense because it's across from the largest side. Does that make sense to everybody? Does anybody have a question on that at all? All right, let me show you another example. That was an example of if you're given two sides in the included angle. Let me show you an example if you're given just all three sides, what to do. Okay. So let's make sure my paper's all lined up here. Let's take a look at, all right, let's take a look at another example. What if I gave you this? Okay, I told you that here we have our A, we have our B, we have our C. If I told you that this was 5, this was 10, and this was 12, and I asked you to solve the triangle, right? Notice again that you do not have any sort of law of sines thing going on here, right? There's no angle and side that are across from each other. So there's really, I'd like to use the law of sines because it's nice and simple, but there's no way to really go ahead and get started with that. So we do have to use the law of cosines. If you're going ahead and doing a side problem where you're given all three sides, it's almost the opposite, where for a law of cosines, we want to start by finding the largest angle. Okay, let's start by finding the largest angle. By starting that way, it will eliminate the ambiguous case from coming up, because we can say, oh, largest angle across from largest side. So I'm happy with that. Okay, so let's do that by solving for angle C. You can use our law of cosines by saying C squared equals A squared plus B squared minus 2AB cosine C. Right, let's now just fill in that information. 12 squared should equal, that's C, A squared is 5 squared plus B squared, 10 squared, minus 2 times 5 times 10 times cosine of C. And I don't know what C is, so we're going to have to isolate that and take the cosine inverse of both sides. We get 144 is equal to, I got 25 plus 100, so 125 minus 2 times 5 is 10 times another 10, so minus 100 cosine of C. We got to get that cosine C by itself, so let's go ahead and subtract the 125. Again, remember, do not combine these like terms. Very tempting to want to do that. Don't do that. Okay, 144 minus 125 is something that I should be able to do in my head, but for whatever reason, I'm so focused on this right now that I pulled the calculator. I apologize. I get 19 is equal to negative 100 cosine of C. You divide both sides by negative 100, you're going to get negative 0.19 is equal to cosine of C. And by the way, it's okay that you get a negative value for cosine because remember, cosine, unlike sine, is positive here, negative here, negative here. So the fact that you're getting a negative value for the cosine means that your angle has to be obtuse, right? Notice that, because it has to be in the second quadrant, you wouldn't have to worry about any ambiguous case for the for cosine, by the way, because it's not possible within the dimensions of a triangle to get anything in the fourth quadrant. Your angles of a triangle have to total 180 degrees. Angles down here are in the like 270 to 360 degree range. So you would never have to worry about anything like that if you're dealing with triangles. That's why we're only focused on the top two quadrants when we deal with triangles, because we're all less than 180 degrees, right? So now I go to my calculator. I do the cosine inverse of negative 0.19. And you get that your angle should be about, we'll call it about 100.9.95 rounds up. We'll call it 101 degrees, just to make it easy. Okay? Does everybody see that? Now we can go ahead and use law of sines for the rest. What I would do, just like before, is I would, so now use law of sines for the rest, often abbreviated as LOS. Okay? I would now go ahead and solve for my small angle first, just like I did going forward. I would say the sine of 101, the sine of C over C, sine of 101 over 12, equals sine of A, which I don't know, over 5. Okay? I'd cross multiply. I'd get 5 sine of 101 is equal to 12 sine of A. Divide both sides by 12. You get 5 sine of 101 degrees over 12 is equal to the sine of A. In order to get rid of the sine, I need to apply the sine inverse on both sides. So, once again, handy dandy calculator. Let's do the sine inverse of 5 sine of 101 divided by 12. Again, ensure that your calculator is in degree mode when you do this, and you'll get that angle A is about, we'll call it 24, what was it, 0.1? 0.1. And now that you know that, by the way, now that you know that this is 24.1, you could find angle B very quickly by just doing 180 minus 101 minus 24.1, because you're just trying to find out like what's left over now that we need for the other angle. And so you would do 180 minus 101 minus 24.1, and we get 54.9. Say angle C is equal to that, so angle C would be 54.9. Okay. Oh, angle B. Sorry, not angle C. Angle B. Okay. Cool. Does that make sense to everybody how the law of cosines works? I know we went right up to the end here, but hopefully that makes sense. Really, it's just another way to solve for missing sides and angles of a triangle, and it really should be employed when you cannot use the law of sines, because the law of sines is much easier and much faster. Law of cosines is this big, old formula that takes forever, but sometimes you just don't have any choice. When you're dealing with all three sides, you don't have an angle that's across, so you can't do the law of sines. And it's the same thing for the previous example, where you saw that we started with this side, and this angle. Nothing is across from each other, so we can't make use of that law of sines right away. Okay? So that's when we need to bust out the law of cosines. When you do the law of cosines on this side angle side case, you do want to make sure that you find the acute angle first. That will help avoid, you want to find, my fault, I misspoke. When you do this side angle side case, you want to find first, using law of cosines, the side that's across from this angle. After you do that, and now you're ready to transition to the law of sines, that's when you want to find your acute angle first, because that will help avoid any results that don't make sense or ambiguous cases from showing up. When you have your three sides, your side, side, side case, you should start by using law of cosines to find the largest angle. Just get that big obtuse angle out of the way. Get it, or it might not be obtuse, but just in case it is, get it out of the way. Once you do that, you can just go ahead and very directly solve for the other angles. You don't have to worry about that ambiguous case now because you've already established what this big angle is. So how can you possibly have any other obtuse angles if you already have one, right? A triangle can only have one obtuse angle because it has to total 180 degrees. Whew, that was a lot of explanation, but hopefully that all made a lot of sense. If you do have any questions or comments, please feel free to let me know. I appreciate you staying just a couple minutes over our deadline here. Again, I talked to you about all that assessment stuff prior to when we started our video lesson, so if you have any concerns about that, do not hesitate to raise them. I'd much rather hear your concerns now than when it comes time for the test and then all of a sudden everybody's like in a frazzle. So please let me know if you have anything, but other than that, I hope you enjoy the rest of your day. All right, and thank you for your attention and focus. Good luck. There's more homework problems due next class, so please make sure you get those done. Have a fantastic rest of your day, everyone, and a great lunch. And I won't see you on Friday, so have a great weekend.